Okay, let's unpack this. Understanding the world around us, it so often means understanding its geometry, how things fit together.
Absolutely. Think about molecules. A protein's function. It depends entirely on its incredibly complex 3D shape.
Right, or RNA structures, point clouds describing tiny particles, or even whole buildings. It's all geometry.
But trying to model these things, predict their behavior using AI, especially when they get really large, thousands, maybe millions of components.
You hit a wall, a massive computational wall.
And it's not just about size, is it? It's making sure your model, well, plays by the rules of physics and chemistry.
Yeah, like if you rotate a molecule in space, its actual properties don't just change.
Exactly. So the model's understanding, its representation of that molecule needs to reflect that. That's the core idea of equivariance.
Equivariant. So the model's output changes predictably if you rotate or move the input.
Precisely. For 3D systems, we talk about SCO3 equivariance. That covers rotations and translations.
Makes sense. If your model isn't equivariant, you might get different answers just based on how you happen to look at the molecule, which is
Not very helpful, no. Useless, really, for understanding real systems.
okay. So the problem is keeping the strict equivariance and being able to see the whole picture, the global context.
For very large inputs, that's computationally brutal.
So our sources, these papers and notes we're diving into, they really highlight this dilemma.
They do. Historically, you kind of had two main camps trying to solve this.
Right.
On one side, you had methods like equivariant self-attention. Think models like Equiformer, G-transformer, maybe.
And these are good because they everywhere, global interactions.
Yeah, they let every part of the system influence every other part. Great for capturing that global context, and this is the sources stress.
Let me guess, the cost.
Exactly. They suffer from quadratic complexity. That's OAV n being the number of bits in your system.
So double the size, 4 times the work.
You got it. It just explodes, becomes impossible for really large molecules or structures. Memory use too, not just compute time.
Okay, so global context, but at a potentially impossible cost. What was the alternative then?
The other camp, they focused on local methods. Things like distance-based message passing. You might have heard of EGNNs, SCHNET, TFN.
Yeah, those are usually much faster, right?
Much more efficient, often linear complexity, ON. So they scale way better. But there's a trade-off.
They can't see the big picture.
The sources say it clearly. They sacrifice global information. They're stuck looking at local neighborhoods.
So they miss how distant parts of a big molecule might interact, which could be really important for, say, how a protein folds or something.
Exactly. Vital for those kinds of complex dynamics. So you were stuck. Either get the whole picture but pay a fortune in computation, or be efficient but miss the long-range stuff.
A classic bind. And that's the challenge this research we're looking at tackles head on.
Which brings us to the main event. The Geometric Hyena network.
Geometric Hyena, okay.
It's presented as, well, a new way forward. The paper calls it the first equivariant long-convolutional model for geometric systems.
Long-convolutional, that rings a bell, like those recent advances in language models for handling really long sequences, moving past standard attention.
That's exactly the inspiration, taking those ideas, that efficiency for long-range stuff, and figuring out how to make it work for complex geometric data.
While keeping that crucial equivariance.
Without sacrificing equivariance, that's the key. The promise here is capturing global geometric context at sub-quadratic complexity.
Meaning much faster, less memory hungry than that ONS self-attention for big inputs.
Significantly. The sources give some pretty striking numbers. Processing 30,000 tokens 20 times faster, using 50 times less memory compared to equivariant self-attention.
Wow.
And potentially handling sequences or context 72 times longer. That's the kind of leap you need for tackling those really big real-world systems.
Okay, those numbers definitely get your attention, but how? How does it actually manage that? Getting global context efficiency and equivariance, especially with 3D vectors like coordinates flying around. This is the core innovation, right? The academic bit.
This is really where the cleverness lies, the technical contribution. Let's start with the input. It's designed for what they call ordered geometric graphs.
Ordered? Like
biomolecules, RNA, proteins. They have a natural backbone, a chain structure. Often you can define a canonical ordering, maybe following IUPAC rules for the sequence.
okay, so there's a defined sequence to the elements, like atoms.
Right. And each element has features. Some are scalar, like atom type. Those don't change if you rotate the molecule. They're invariant.
But others are vectors, like coordinates, maybe velocities.
Exactly. And those do transform when you rotate or translate the system. They're equivariant.
So you've got these two kinds of data behaving differently under geometric transformations.
And the architecture respects that. It uses dual streams. One stream processes the invariant scalar stuff. The other handles the equivariant vector stuff.
Keeping them separate helps maintain the overall equivariance.
That's the idea. Ensure the whole model respects the geometry, layer by layer.
Okay, dual streams. But where does the global context engine come in? The efficient part.
That's the geometric long convolution. This module is the replacement for the computationally heavy self-attention layer you'd find in equivariant transformers.
It aggregates information across the whole sequence using convolution, but somehow adapted for geometry.
Exactly. And it handles both the scalar and vector features.
But wait, isn't convolution usually a local operation? Looking at neighbors, how does it become long or global?
That's where they borrow the trick from those efficient sequence models. For the invariant scalar features, they use scalar long convolution.
Okay.
This leverages the fast Fourier transform, FFT. FFT-based convolution is a well-known, super efficient way to compute convolutions over very long sequences. It gets you down to OM log n complexity.
Right. FFT convolution for long sequences is a standard technique. ON log n is much, much better than ON.
Definitely. That part's similar to the original Hyena idea for sequences.
Okay, efficient scalars via FFT, got it. But applying that same efficiency to the equivariant vector features, that sounds like the really tricky part. How do you do a global equivariant convolution for vectors that's also fast, like ON log n?
And that is the novel technical achievement here. This is the core academic contribution, I think. They developed the equivariant vector long convolution.
Okay.
Instead of using dot products like in scalar convolution or attention, they built this operation around the vector cross product.
The cross product between vector queries and keys across the sequence.
Yes, the cross product is fundamental here because taking the cross product of two vectors naturally produces another vector that transforms correctly under rotation. It inherently respects equivariance.
That makes geometric sense, but computed cross products between vectors across an entire long sequence efficiently. Using FFT, how does that work? It sounds complicated.
This is the really elegant part. They found a way to break down this seemingly complex global vector operation into a series of much simpler, efficient calculations that can use FFT.
Decompose it. How?
The insight is that the components of the output vector from this cross-product convolution can be expressed using combinations of scalar convolutions between the individual components, x, y, z, of the input vectors. Through some clever math using something called the Levi-Civita symbol, they show that to get the final three components of the output vector, you only need to perform 6 specific scalar convolutions between the different components of the input vector queries and keys.
Wait, just 6 scalar convolutions? They turned one big complex vector convolution into 6 standard efficient scalar ones.
Exactly. And since each of those 6 scalar convolutions can be computed efficiently, using FFT in ON log n time.
The whole equivariant vector long convolution layer also achieves ON log n complexity.
Precisely. That decomposition is the key technical trick. It allows them to get the geometrically correct operation, equivariance via cross product, but compute it using highly efficient existing methods. They sidestep the need for more complex, computationally demanding approaches, like using spherical harmonics or Clech-Gordon coefficients, which the sources mention as alternatives.
Wow. Okay, that is clever. Using known efficient scalar tricks to compute a necessary but complex vector operation while keeping the geometric rules intact. That's a neat piece of engineering.
It really is. And the model doesn't just keep the streams totally separate forever. There's rich invariant equivariant interaction. The geometric long convolution combines results, so scalar info can influence vector outputs and vice versa.
Modeling things like scalar-scalar interactions, vector dot products, scalar-vector products.
And that crucial vector cross product, all handled efficiently in Cartesian space.
So the how is dual streams, this really innovative, decomposed geometric long convolution using FFTs. Were there other tweaks needed to make it work well in practice?
Yeah, the sources mentioned a few important refinements. One is how they handle the initial projection, the first layer. It's called equivariant projection with context.
Okay.
It uses a modified approach, kind of inspired by local graph networks like EGNNs, but it mixes local message passing info from immediate neighbors with information from global context tokens.
Global context tokens, like summaries of the whole structure?
Sort of, yeah. Learn summaries of features across the whole graph weighted by a small neural network. The idea is to give the model an early sense of both local details and the overall picture.
So it gets a feel for the neighborhood and the global shape right from the start.
Right. The paper notes this mixing, this alternating local-global processing actually helped improve convergence. It echoes findings in other graph networked areas.
Interesting. What else?
There's also selective dating. Basically a mechanism that learns to dynamically emphasize or mask out certain tokens as information flows through the network.
Like a soft attention, letting the model focus on the most relevant geometric bits.
Kind of, yeah. It uses an equivariant projection and a sigmoid function to achieve this. And finally, something highlighted as a critical step for just making it trainable.
Ah, the unsung hero. Numerical stability.
You guessed it, key value normalization when you're doing these long convolutions, multiplying features over and over.
Things can blow up, magnitudes can explode.
Exactly. They found that without normalizing the keys and values involved in the convolution to have a unit norm, the output magnitude could grow cubically, like m cubed. That makes training unstable, especially if you want to use decent learning rates.
So normalizing keeps it under control.
Yeah, it limits the growth to just m, making the whole training process stable. Critical, they say.
Okay, so the recipe is dual streams, the clever decomposed geometric long convolution, mixed local global input projection, gating, and careful normalization. That's the technical heart. How did it actually perform on real tasks?
Right, theory's great, but does it work? The paper shows experiments on several pretty challenging large-scale molecular data sets.
Like what?
They looked at large RNA property prediction, using data sets like Open Vaccine and Rebonanza 2K, predicting things like the stability or degradation profiles for RNA molecules. Some of these have thousands of atoms.
Tasks where you'd expect global structure and long-range interactions to be super important.
Definitely. And Geometric Hyena achieved better accuracy, lower prediction error, or RMSE, compared to other state-of-the-art equivariant models, up to 15% better on some metrics.
And the efficiency, did it hold up in practice?
Oh yeah. The benchmarks are pretty stark. For a sequence with 30,000 tokens, Geometric Hyena was, like we said, 20 times faster and used 50 times less GPU memory than the leading equivariant self-attention models.
That's huge.
And here's the kicker. It could handle sequences up to 2.7 million tokens in their tests. The equivariant transformer baseline, it ran out of memory around 37,000 tokens.
Whoa, so Geometric Hyena could process structures roughly 72 times larger while still considering global context.
Exactly. That's a genuine game changer for the kinds of systems you can even attempt to model globally.
It opens up whole new areas. What else did they test?
They also applied it to RNA switching factor prediction on a dataset called TC-REBO, where it was competitive with the best existing global equivariant methods, and also protein molecular dynamics, predicting how protein atoms move over time.
Another classic hard problem.
Yeah, and there it reduced the prediction error, the MSE, compared to the next best model. So consistent good performance across different kinds of geometric problems.
You mentioned they introduced a new task too, geometric associative recall. What was that about?
Ah, yes, that was interesting. They designed this task specifically for mechanistic interpretability, basically trying to understand if the model is really learning and using the geometric context correctly.
How does the task work?
It's set up like this. The model sees a sequence of points, each with some associated vectors. It has to find a specific value vector associated with one point, based on a query vector at another point, and may be guided by a key vector somewhere else. The crucial part is, it has to do this correctly, even if you rotate or translate the whole sequence.
So it's like testing its geometric memory. Can it retrieve the right geometric feature from way over there, based on a cue from here, while respecting the overall geometry?
Precisely. Can it perform context-dependent retrieval in an equivariant way? And Geometric Hyena learned this task very well, significantly better than most other baselines, including other equivariant models.
Why did it do so well there?
The authors suggest it's down to that unique architecture, especially the blend of local processing from the initial projection and the global context from the long convolution. That combination seemed key.
The results showed it was pretty robust too.
Yeah, the figures show its errors stayed low and stable, even as the sequence length increased, and it performed well even with smaller model sizes where others started to struggle. It really highlights its ability to use geometric context effectively.
Okay, so efficiency breakthroughs, strong real-world results, and this demonstrated ability to learn geometric context. What are the catches, the limitations?
The main one, which the authors acknowledge up front, is the dependence on canonical ordering.
Oh, right, because the efficient FFT convolution works on sequences.
Exactly. FFT isn't inherently permutation equivariant. It assumes a sixth order. This works fine or well enough for things like proteins or RNA, where you have a natural backbone sequence, a conventional way to order the atoms or residues.
But what about data that doesn't have a natural order, like a point cloud just describing a jumble of particles or points scanned from an object?
That's the issue. For arbitrary point clouds, establishing a consistent, meaningful canonical order is difficult, sometimes impossible. And without that reliable order, The FFT-based efficiency of the long convolution can't be fully leveraged while also being invariant to how you happen to list the points.
So its current strength is really tied to inputs that have that inherent sequence-like structure.
That's the main constraint right now, making it work efficiently for unordered geometric data. Achieving permutation equivariance, perhaps through different means, is flagged as important future work that would really broaden its applicability.
Okay, got it. So let's bring this home. The core takeaway here seems to be that Geometric Hyena is a pretty significant step forward, both academically and practically.
Absolutely. It's successfully brought these powerful, efficient, long convolution ideas, which were transforming sequence modeling, into the really challenging world of geometric deep learning, where you also have to obey the laws of physics through equivariance.
And it really tackles that long-standing trade-off, right, between computational cost and capturing the global picture for large geometric systems.
Yeah, by being sub-quadratic, O and log n, while staying strictly equivariant, it makes it feasible to model systems that were simply too big for previous global methods.
We're talking potentially 70 times larger context, 50 times less memory. That's not incremental.
Not at all. And its performance on those real-world molecular tasks, plus the new recall task, shows it's not just efficient, it actually works well and seems to genuinely learn and use the geometric context.
So for you, the listener, the bottom line is that AI is getting much, much better and dramatically more efficient at understanding the complex 3D world. Molecules, materials, anything where shape and spatial relationships are key.
Which could really speed things up. Think drug design, discovering new materials, even understanding fundamental physical simulations better. Anywhere geometry at scale is the name of the game.
So thinking about that, given this new power, this efficiency, especially the ability to process geometric context globally at scales that were just out of reach before, what other really complex, large-scale geometric systems might now be modelable? Things in biology, chemistry, physics, engineering that were just too big, too intricate for AI until now.
Yeah, what new scientific questions can we finally start asking now that we can potentially handle geometric data globally at this unprecedented scale? What might we discover?
It definitely feels like it opens up some exciting new possibilities.
It really could shift the landscape for scientific AI.